Okay, so the first thing is test one is a week from today. So I started this right. Yes. So Wednesday, February 5th. And the topics are going to be everything up through vectors. So there won't be any two-dimensional kinematics, but all of the problems in the set that say vectors, there'll be questions like that on there, and then everything before. Okay. To get ready for the test, it's really just about understanding those problems. So there's not going to be any short answer stuff like the quiz. It's all going to be problems using the same thought process that you use in the ones that were assigned. Okay. Anybody have any questions about the test? Okay. Anybody have any homework questions? Yep. Oh, I didn't bring the questions with me. Anybody have the set on vectors? Yeah. Okay. Anybody? Okay. Oh, I got it here. Thanks. Okay, so it gives you a vector with a length of 50. And it says the vector makes an angle of 30 degrees with the horizontal. So this angle is 30. And we want to come up with the components. First in our usual coordinate system. And then second in a rotated coordinate system. Where the x-axis is up and the y-axis is to the left. Okay, so first put down the coordinate system that you have. So this is the one for part A. And then put the vector down without rotating. So you're never adjusting the vector. The vector is the direction it is. And I'm going to put the tail at the origin of the coordinate system. So we have a length of 50. And the angle that's given says that there's a 30-degree angle between the horizontal and the vector. So this angle is 30 degrees. And now we're trying to figure out the counterclockwise angle from the positive x-axis to the vector. Well, that happens to be what's given in this case. So the theta for this is just positive 30. And then the components are 50 times the cosine of 30, 50 times the sine of 30. And that is 43.3, 25. You could also just, I mean, in this case, it would be the same thing, but you can always think about it in terms of SOHCAHTOA and just think about the signs, the plus minus signs of the components based on what quadrant you're in. So in the first quadrant, you know you're going to have 2 positive components. Second quadrant, negative x, positive y. Third quadrant, 2 negative components. And fourth, positive x, negative y. And just make the right triangle and figure out the legs and then put the signs on. Okay, so the second one, part B, our coordinate system has the positive x-axis up and the positive y-axis to the left. We still don't rotate the vector. We just like it's drawn, we put the tail at the origin, and it still has a magnitude of 50. And the angle that we're given is that this is 30 degrees. But now that's not 30 degrees counterclockwise from the x-axis anymore. That's from, this is the negative y-axis now. So we need to figure out the angle going counterclockwise all the way from our new x, our x for this problem, to the vector. You could also go clockwise and call it a negative angle. So if you go counterclockwise, it's 90, 180, 270, plus 30 is 300. Or if you go clockwise, 30 plus the angle we want, add up to 90, so it's negative 60. And either way you do it, it'll give you the same answers. So 50 times cosine of 300, 50 times sine of 300, same as negative 60. And you get 25 negative 86.6. So you can also think of it as, draw the right triangle. You're given that this angle is 30 degrees. The length is 50. And so 50 times sine of 30 degrees gives you this component. $50 times cosine of 30 degrees gives you this component, this leg length. And then you just look, this is the one in the x direction, the 25. The 86.6 is the one in the y direction, and it's negative. So you get the same thing. Any questions about that? Yes?
So when you rotate the axis, the positive x and positive y kind of stay and everything shifts.
When you do, yes. So the x and y always have to keep the same relationship. All you can do is rotate that around.
Gotcha.
Yep, exactly. Yes.
The 86 would not really work for that length because
yes.
Get a length of 90 instead.
Yeah, I used the wrong number. It's the 43.3. Thank you. $43.3, and same thing with this. I multiplied by 100 instead of 50.
I was like, hold on, how is all the legs longer than the hypotenuse?
Yeah. Because the other leg is imaginary. Any other homework questions? All right, so let's go back to vector stuff. So last time, first we talked about vector addition and multiplying a vector by a scalar thinking about the physical meaning. And then we talked about how to calculate vector components. So now we're going to do vector addition and scalar multiplication of vectors using the components. And this is the way you're going to do it mathematically. You're not going to do it geometrically. Okay, so when we do this stuff using components, we've already talked about what the meaning of adding vectors is. So this component approach needs to match that physical approach. So first, adding vectors. So let's say that you have a vector AB. Those are the components. And you're adding it to a vector with components CD. And we want to know the components of the sum of those vectors, the resultant vector. And the answer is you just add up the x components, and that's your new x component of the resultant vector, and add up the y components, and that's the y component of your resultant vector. And you're done. And that simple way of doing component addition means the same thing as that physical meaning of vector addition that I told you about last time. Notice that the order doesn't matter. Just like adding two numbers together, if you have a vector A and you add it to a vector B, that's the same thing as a vector B and adding a vector A. And these arrows mean that we're talking about a vector variable. So if there's an arrow over the top of a variable, that means that variable can be broken up into components. Okay. So that means that when you're talking about the components of these vectors, you don't use the vector symbol. Like here, A, B, C, and D are just numbers. And together, those components make up a vector. And the second thing that we'll have to do is multiply a vector by a scalar. And this has to have the meaning that the physical meaning that I gave last time too, and it does. So let's say that we have a number C that we're multiplying to a vector with components A, B. what you do is multiply the number to each of these components. So the x component of the product is CA, and the y component of the product is CB. Okay, so let me use these in a problem. So let's say we have a vector so let's say we have a vector with a length of 2 that's straight up. Let's say this is what we're going to call the vector A. And then we have a vector with a length of 4. Where this angle is 20 degrees. And let's say this is the vector B. And now let's say that the coordinate system has x up and y to the left. And we want to know what are the components of the vector 3a minus b. In this coordinate system. Okay, so the way we're going to do this is first we're going to calculate the components of these two vectors in this coordinate system. Okay, and then we're going to use the rules for adding and multiplying with vector components. So here's the coordinate system. There's x, there's y. And there are two vectors that we care about. One goes this way and has a magnitude of 2. And then the other one goes this way and has a magnitude of 4, where this angle is 20 degrees. So first A, there are two ways to think about, like if you ever have vectors that just go along one of these 4 axes, you can just, well, like how you go 2 in the straight x direction in terms of a trip along x and a trip along y. First you go 2 along x, and then you don't go anywhere. You're already there. So this is only going to have an x component of 2 in the positive direction. So positive 2, 0. Okay, you can just eyeball the ones that are on those 4 axes. Okay, so A is just positive 2, 0. You could also think of that as the angle is 0 degrees. And they would be 2 times cosine is 0, 2 times sine is 0, and it gives you the same thing. But you can just do those right off the bat. And then for B, what's the counterclockwise angle from the positive x-axis to that vector B? Yep. positive 70. So this is 4 times cosine of 70, 4 times sine of 70, and that, I can't do that in my head. What, can someone calculate 4 times each of these two?
First one, x is 1.368.
Okay.
And the y is 1.799.
Okay, so now we have both of those in components. Now we're going to go 3 times the components of A minus the components of B it follows the same rules of operation that you're used to with numbers. So first we have to do the multiplication, then we do that subtraction. So 3 times 2 is 0. No, it's not. 3 times 2 is 6. 3 times 0 is 0. Minus 1.368 and 3.759. And that gives 4.632. And this one is negative 3.759. And if you went through the effort of carefully on graph paper, doing 3 times this one, and then using the rules of vector addition, and then the opposite of this one, then use the rules of vector addition to add those two things together. And then you carefully plotted out this vector in this coordinate system, the two approaches would match. But the component approach is way faster. Okay. There are two other things that we'll sometimes need to do with vectors. Calculate the magnitude of a vector where you know the components, and take derivatives and integrals of vector components. So 2 more calculations with vectors. The first one is to calculate the magnitude of a vector from the components, so the length of the arrow. And the second one is time derivatives and integrals with respect to time of vectors. Okay, so to calculate the vector magnitude, if you have a vector, I'll call this vector U that has components A, B. Then the magnitude, which uses the notation is like an absolute value of a vector. That's the magnitude of a vector. And the way you calculate that is the square root of the sum of the squares of the components. And it makes sense if you think about the vector and the components making up a right triangle. If this is A and this is B, and this is the magnitude of the whole vector, then it has to satisfy the Pythagorean theorem. And next, calculus operations. And this is something that you don't have to worry about in this class, but it is something that sometimes you have to worry about. So I'm going to, in parentheses, say in non-rotating coordinate systems. So if your coordinate system is rotating over time, then it's more complicated to do time derivatives than what I'm going to show you. But we're not going to have to worry about that here. So the way you do that is just do the calculus operations on the individual components. So the time derivative of a vector u I'm going to move this down. So let's say that we have a vector u again that's A is the x component, B is the y component. Then to take the time derivative of that vector, you just take the time derivative of the x component, and that's the x component now of the derivative. And the y component is just the time derivative of the old y component. Same idea for the integral. So the integral of u dt is just the integral of a dt for the x component and the integral of b dt for the y component. Okay, so let's say that we have a vector u that's a function of time. And let's say that the x component is 5t and the y component is negative 2t squared. So first, let's calculate u dot at time equals 2. And second, let's calculate the integral of u dt at time equals 1 second, or whatever units of time you're using. Well, u dot as a function of time is 5 for the x. We're just taking derivatives with respect to time. Negative 4t. And now we want to evaluate that So U dot evaluated at time equals 2. Just plug 2 in for these, and you get 5 for the x component, negative 8 for the y component. For the integral of u as a function of t dt is 5/2. Oh, you know, did I give boundary conditions here? Well, okay, let me just do it the way I have it written. So 5/2 t squared plus some constant of integration, because I'm integrating this one, not the derivative. And then negative 2t cubed over 3 plus some constant c2 . If we want to evaluate this at time equals 1, we would get 5/2 plus c1 and negative 2/3 plus c2. The c1 and the c2 are unknown constants of integration. So how would we calculate those? What? We'd need to be given boundary conditions at the start of the problem. So we can't find C1 and C2 unless we're given boundary conditions. Like, for example, that the integral of u at time equals 0 is equal to 5 for x and 6 for y or something. Any questions about that? Okay, so how would you guess? Can you think of a way based on the physics we've done so far, before we got to vectors, how would you think calculus is going to come up with vectors when we go to two-dimensional kinematics? Yep. Yeah, that's exactly right. So just like with kinematics along a line, we had the relationship that velocity is equal to the time derivative of position, and acceleration is the time derivative of velocity. Okay. Now position, velocity, and acceleration are all going to be vectors. That's a new thing. But we're still going to have the relationship that the velocity vector is the time derivative of the position vector, using this definition of calculus with vectors. And the acceleration is still going to be the time derivative of the velocity vector. Okay. So the first thing, before we can start doing kinematics using vectors, the first thing I have to do is define what these kinematic quantities mean. By the way, this point here is the end of material for the test. So now we're going to go on to two-dimensional kinematics of particles, and that is not relevant for the test next week. Okay, so kinematic quantities as vectors. So now in 2D, position, displacement, velocity, and acceleration are all vectors. And so I'm going to define these one by one. And I'm not going to talk about the units for them individually like I did before. The units are just the same as they were in one dimension. So SI units for position are meters. SI units for displacement are meters. For velocity, meters per second. For acceleration, meters per second squared. The only difference is we'll give these as pairs of components. Okay. So the first thing we have to define is the position vector. And to give position vector components, you must first choose an origin location and a coordinate system orientation. Okay, so this position vector is not defined until you make these two choices. Is that familiar at all? That's analogous to what we did in one dimension. These are like the 2D version of the zero position and the positive direction. So once you choose those, so say even before you choose them, you know, the object that you're tracking it exists, that it's going to exist whether you're there measuring it or not. But once you choose where the coordinate system is and the orientation of the X and Y axes, the position vector is the vector that goes from the origin of the coordinate system to the object. So this is the position vector. Another way to think about that it is that the position vector components are the coordinates of the object. All right, well, usually we're going to want to know the position vector as a function of time. So what else do we have to specify? What else do we have to choose before we can define the position as a function of time? Yep, exactly. So if you also choose a time equals 0 instant, then you can represent the position vector as a function of time. And I'll write that. So there's the position vector. It's a function of time. And I'm going to break this down into an x component as a function of time and a y component as a function of time. Sometimes you'll also see it as px, the x component of the position, and py as a function of position. Those mean the same thing. Any questions about that? Okay. Well, let's stop there, and next time we'll do velocity and acceleration, talk about how to interpret those. Yeah. And if you have any questions about homework or whatever, bring them tomorrow. Questions that are relevant to the test or anything like that, I'd be happy to answer them.